Hello everyone, and a very warm welcome to today's presentation. I'm excited to have you here. Today, we'll be discussing the calibration of UV-visible spectrophotometers. The presentation is titled Calibration of UV-Visible Spectrophotometer and is presented by Dr. S.K. Singh, Ph.D. I'll be guiding you through the key steps and best practices to ensure your spectrophotometer is properly calibrated for accurate measurements. Over the next few slides, we'll cover the essential procedures, common challenges, and tips for maintaining your instrument's precision. Let's get started. Let's dive into the purpose of calibration. The main goal here is to ensure that our analytical data is both reliable and accurate. This is critical because, in our industry, the quality of our results directly impacts product safety and efficacy. Calibration isn't just a routine task. It's a key element for compliance with various regulatory standards like USP 857, ICH Q2, R1, FDA 21 CFR, and GMP or GLP guidelines. These standards set the baseline for how we validate and verify our instruments and processes. Now, speaking of regulatory standards, USP 857 focuses on performance verification of UV-vis instruments, making sure they're functioning properly. ICH Q2, R1, on the other hand, is about validating our analytical methods, checking for accuracy, precision, and linearity to ensure our methods produce consistent and trustworthy results. And then there's 21 CFR Part 211, 160b, 4, which emphasizes the importance of maintaining detailed calibration records. These records are vital for traceability and compliance during inspections. Moving on to UV-vis spectrophotometer calibration. Specifically, calibration involves verifying the instrument's performance against certified reference standards, or CRMs. This process helps us confirm that our instrument is measuring correctly and consistently over time. Why does this matter so much? Well, calibration helps us detect issues like wavelength and photometric drift, stray light interference, or resolution problems before they impact our data. This proactive approach ensures our quantitation is accurate, which is essential for the validity of our assays and their validation. In essence, calibration keeps our instruments trustworthy and our data dependable, supporting the overall integrity of our analytical work. Let's take a closer look at the key calibration parameters we need to focus on. These are outlined by USP 857 and are also considered best practice across the industry. First, we have wavelength accuracy, which ensures that our instrument is measuring at the correct wavelengths, a critical factor for reliable results. Next is absorbance or photometric accuracy. This confirms that the absorbance readings are precise and trustworthy. Stray light is another important parameter. It refers to any unwanted light that can affect our measurements, so controlling it is vital for accuracy. Resolution is about the instrument's ability to distinguish between close or overlapping signals, which is essential for detailed analysis. Baseline flatness and noise relate to the instrument's stability, how steady and noise-free the baseline remains during measurements. Lastly, photometric linearity, though optional or for expert judgment, verifies that the instrument's response is linear across a range of concentrations, which is important for quantitative results. All these parameters work together to ensure our calibration is solid and our data is dependable, reinforcing the overall integrity of our analytical process. Let's look at this example to understand wavelength accuracy. Here, we have a certified peak at 287.15 nanometers and a measured mean of 286.7 nanometers. The difference between these two is 0.45 nanometers, which falls within the acceptable range, so this test passes. The main goal here is to confirm that our monochromator is reading the correct wavelength, or lambda, values. To do this, we use a standard, specifically a holmium oxide filter or solution that's certified for accuracy. The procedure involves scanning a range of specified wavelengths, typically from 240 to 650 nanometers, using our calibration reference material. We then measure the peak positions in nanometers for each scan. Acceptance criteria, according to USB standards, specify that in the UV range, from 200 to 400 nanometers, the readings should be within plus or minus 1 nanometer. For the visible range, from 400 to 900 nanometers, the tolerance is plus or minus 2 nanometers. Additionally, to ensure precision, we perform 6 replicates and look at the standard deviation, which should be less than or equal to 0.5 nanometers. This process is critical because accurate wavelength readings are fundamental to the quality and reliability of our spectroscopy measurements, tying back to our overall theme of maintaining rigorous analytical standards. Let's talk about absorbance accuracy, which is a key aspect of ensuring our measurements are reliable. The main objective here is to verify that the absorbance readings we get match what's expected from certified standards. To do this, we use standards like potassium dichromate or nicotinic acid CRMs, which are well-characterized reference materials. In practice, we measure the absorbance at specific wavelengths that are important for our analysis, say 235, 257, 313, and 350 nanometers. It's important to take multiple readings, 6 replicates at each wavelength, to ensure consistency and accuracy. Now, when it comes to acceptance criteria, the USB provides clear guidelines. For absorbance values between 0 and 1, our readings should be within plus or minus 0.01 absorbance units. For higher absorbance readings, from 1 to 3, the variation should be within plus or minus 1%. Additionally, we look at the precision of these measurements. The standard deviation should be less than or equal to 0.005 absorbance units when the readings are between 0 and 1. For higher absorbance ranges, the variation should be within 0.5%. Overall, this process helps us confirm that our spectrophotometric readings are both accurate and precise, which is essential for the quality and consistency of our analytical results. Let's talk about stray light. This is basically unwanted radiation that shows up at wavelengths where we expect high absorbance, like below 220 nanometers. It can be a real problem because it skews our measurements. To keep things consistent, we use a standard, 1.2% potassium chloride or sodium iodide. When measuring absorbance, we typically use water as a blank to calibrate our instrument. The acceptance criterion is that the absorbance should be at least 2 absorbance units, at around 198 to 200 nanometers. Now, why does stray light matter? Well, it directly affects the accuracy of our results, especially when we're analyzing low wavelengths where precision is crucial. High stray light levels can make our data unreliable, so it's important to monitor and control it carefully throughout our analysis. Now, let's talk about resolution, which is a key concept in our analysis. The main objective here is to be able to distinguish 2 peaks that are very close together. This is crucial for accurate identification and quantification. To meet this standard, we are working with a sample of 0.02% VV toluene in hexane. The procedure involves scanning the spectrum from 260 to 270 nanometers, and during this scan, we'll record the maximum absorbance around 269 nanometers and the minimum around 266 nanometers. These peaks tell us a lot about the sample's characteristics. Finally, the acceptance criterion for resolution is an absorbance ratio of at least 1.5. Achieving this ratio indicates that our peaks are sufficiently separated, which confirms that our method can reliably distinguish the components. Remember, good resolution ensures the accuracy and precision of our analysis, aligning with our overall goal of developing a robust analytical method. Now, let's talk about baseline flatness and noise. When we measure the baseline, we typically do this with a blank sample or just air across the entire range. The goal here is to ensure that the baseline variance stays as low as possible. Ideally, we're looking for variations within about plus or minus 0.002 to 0.01 absorbance units. This small variance indicates a stable and consistent baseline. We also measure noise, which we quantify as the RMS deviation, or root mean square deviation. This helps us understand the level of random fluctuations or disturbances in our readings. Keeping noise low is crucial for accurate measurements. Why is this important? Well, these baseline and noise measurements are essential tools for quality control and stability checks. They help us verify that our instrument is performing reliably over time, ensuring that our results are consistent and trustworthy. So, maintaining a flat baseline with minimal noise is fundamental to obtaining precise and accurate data in our analyses. Let's take a closer look at wavelength accuracy. Here, we have some certified peak wavelengths, which are 241.14, 287.15, 361.5, and 536.3 nanometers. These are the reference points we expect our measurements to match. Focusing on the 287.15 nanometer peak, we measured 6 replicate values: 286.95, 287.05, 287.2, 286.85, 287.1, and 287.15 nanometers. These readings are quite close to the certified value, which is promising. Now, to assess the accuracy, we calculate the mean of these measurements, which comes out to 287.05 nanometers. We then find the deviation by subtracting the certified value from our mean. 287.05 minus 287.15 equals negative 0.1 nanometers. Since this deviation is within acceptable limits, we pass this test. Next, we look at the precision by calculating the standard deviation of our replicate measurements. In this example, the standard deviation is approximately 0.12 nanometers, which is well below the maximum allowable deviation of 0.5 nanometers. This overall process, comparing the measured mean to the certified value and ensuring the standard deviation is within limits, helps us confirm that our wavelength measurements are both accurate and precise, which is essential for reliable analytical results. Let's take a closer look at the objective of this step. Our goal here is to verify that the UV visible spectrophotometer is accurately measuring the wavelength of incident radiation across the entire specified range. This is crucial because accurate wavelength measurement ensures the reliability of our spectrophotometric data. Next, we use a standard, specifically a holmium oxide filter or solution, which is a certified reference material. Using this standard helps us compare our instrument's readings against a known, certified wavelength, providing a benchmark for accuracy. The procedure is straightforward but meticulous. We start by scanning the holmium oxide standard over the designated UV visible range. During this scan, we record the observed wavelength maxima, which are the peaks corresponding to the known absorption features of holmium oxide. To ensure precision, we perform 6 replicate scans at each certified wavelength. This repetition helps us assess the consistency of our measurements. From these scans, we calculate the mean wavelength, which gives us an average measurement, as well as the deviation and standard deviation, to evaluate the variability and accuracy. Finally, we use these data to perform a calculation of wavelength accuracy. This step confirms whether our spectrophotometer is performing within acceptable limits, ensuring confidence in all subsequent measurements. This process is integral to maintaining the integrity of our analytical results across the entire measurement range. Now, let's take a closer look at the acceptance criteria according to USP 857. In the UV region, which spans from 200 to 400 nanometers, the acceptable wavelength variation is within plus or minus 1 nanometer. Moving to the visible region, from 400 to 900 nanometers, the tolerance widens slightly to plus or minus 2 nanometers. It's important to emphasize that precision is key here. The standard deviation, or SD, for measurements should be less than or equal to 0.5 nanometers, based on 6 replicate measurements. This ensures our results are reliable and consistent. When we talk about calculating wavelength accuracy, we're essentially verifying that our instrument's readings stay within these specified limits. This step is critical to maintaining compliance with USP standards and ensuring the quality of our analytical results. Overall, these criteria help us confirm that our spectrophotometers are performing accurately and consistently, which is fundamental for generating valid and reproducible data across our testing procedures. Let's take a closer look at absorbance accuracy. This is a crucial aspect because it directly impacts the reliability of our measurements. When we talk about accuracy and absorbance, we're essentially referring to how close our measured values are to the true or actual values. Ensuring high accuracy means our results truly reflect the sample's properties. Factors that influence absorbance accuracy include proper calibration of the instrument, correct sample preparation, and minimizing any potential errors or interference during measurement. Remember, the goal is to have consistent and precise readings that we can trust for further analysis. By maintaining accuracy, we strengthen the overall integrity of our data and the conclusions we draw from it. This ties back to our broader theme of ensuring quality and reliability in our analytical processes. Now, let's look at our main objective here. We want to verify the accuracy of the absorbance measurements from our UV visible spectrophotometer. To do this, we use certified reference standards, which are essential for ensuring our measurements are reliable. The standard we're using in this process is potassium dichromate, or K2Cr2O7, solution. Sometimes, we also use nicotinic acid or other USP traceable CRMs, which are certified reference materials that help us confirm our instrument's accuracy. Moving on to the procedure, first, we prepare the certified absorbance standard according to USP guidelines. This step is crucial because proper preparation guarantees the validity of our measurements. Next, we measure the absorbance at specified wavelengths, making sure to follow the recommended protocol. To get a good sense of the instrument's precision, we record 6 replicate readings at each wavelength. This repetition helps us identify any variability or inconsistencies. After collecting our data, we then calculate the mean absorbance, the deviation, and the percentage error. These calculations are vital because they tell us how close our measurements are to the true value, giving us confidence in our instrument's performance. Finally, through these steps, we assess the absorbance accuracy. This process is a key part of validation, ensuring our spectrophotometer provides accurate and reproducible results, which is fundamental to the overall quality control process. Let's continue our discussion on absorbance accuracy with this next slide. Here, we're diving deeper into some of the factors that can influence how accurate our absorbance measurements are. As we've seen earlier, precision is crucial, but accuracy really ensures that our results reflect the true values. One key point to highlight is that even small errors in absorbance readings can significantly impact our final concentration calculations. That's why it's important to understand the sources of these errors. For instance, instrumental factors like calibration issues or stray light can cause deviations. Similarly, sample handling, such as inconsistent pipetting or sample contamination, can also affect the readings. It's also worth noting that ongoing calibration and validation of the spectrophotometer help maintain accuracy over time. This means regularly checking the instrument with standards and ensuring everything is functioning properly. Remember, the goal is to minimize these errors as much as possible to get reliable, reproducible results. This ties back to our overall theme of ensuring data integrity in our analytical processes. So, paying attention to these details really makes a difference in achieving accurate absorbance measurements. Now, let's discuss out-of-tolerance, or OOT, handling. When an instrument falls outside of its acceptable limits, the first step is to clearly label it as OOT, do not use. This helps prevent any accidental use of an unverified instrument. Next, it's important to investigate the root cause of the discrepancy. Common causes might include instrument drift or lamp aging, but thorough analysis is key to understanding exactly what went wrong. Once we identify the cause, we proceed with corrective and preventive actions, or CAPA, and perform an impact assessment. This often involves retesting samples to confirm whether the issue has been resolved and to evaluate any potential impact on the data or product quality. Finally, after implementing corrective actions, it's essential to repeat the full calibration process. This ensures the instrument is properly calibrated and reliable before it's put back into service. Handling OOT situations diligently is critical because it maintains the integrity and accuracy of our measurements, which ties back to our overall focus on quality and compliance. Now, let's talk about frequency and documentation in our calibration process. First, the frequency refers to how often we need to perform qualification activities. This includes initial qualification when we first set up the equipment, then periodic checks, which are usually done monthly or quarterly, following our SOPs. Additionally, we must perform requalification after any major maintenance to ensure everything remains accurate and reliable. Moving on to documentation, it's essential to keep thorough records of each qualification. This includes the calibration protocol or worksheet, which details the procedures followed. We also need to record raw data, typically 6 replicates, to demonstrate consistency and precision. Results and deviation analyses should be documented to track performance over time. Signatures of both the analyst and reviewer are crucial. They serve as accountability and verify that the work was checked thoroughly. Lastly, we must keep CRM certificates, which confirm that our calibration standards are valid and traceable. All these elements together help uphold our quality standards and ensure the reliability of our calibration system, aligning with our overall goal of maintaining compliance and data integrity. Let's wrap up with some key takeaways and best practices. First, it's important to use CRMs as far as possible, in accordance with USP 857. This helps ensure consistency and reliability in our data management. Next, performing multiple replicates is crucial. It strengthens the validity of our results and reduces variability. Additionally, defining the schedule clearly in your SOP is essential. It keeps everyone on the same page and maintains a structured approach. And finally, always ensure you have documented evidence to support your work, especially for audits. This documentation not only demonstrates compliance, but also helps us track and verify our processes effectively. Remember, applying these best practices helps us uphold quality, accuracy, and integrity throughout our operations. For further support, please don't hesitate to reach out. We're here to help you with any questions or additional information you might need. Remember, the goal is to ensure you feel confident and equipped to apply what we've discussed today. Thank you so much for your time and attention. We truly appreciate your engagement and look forward to supporting you moving forward.